Welcome to this presentation on redox reactions. But before I define the term redox for you, one of my favorite terms in all of chemistry, I want to apply one of the concepts we've talked about in previous videos to this reaction right here. And that concept is the oxidation state, or the oxidation number. And we've learned that oxidation states are really just a way of measuring where electrons are, where they spend their time in chemical compounds throughout chemical reactions. What we're going to do here is we're just going to assign oxidation states to each of the elements in this chemical reaction. This chemical reaction just being the simple combustion of methane, adding some oxygen gas, producing carbon dioxide and water vapor. So let's get going. Hydrogen, of course, generally takes an oxidation state of +1, meaning carbon has to take an oxidation state of -4 to balance the +4 charge from this hydrogen. Elemental oxygen, any atom in an elemental state, takes an oxidation state of 0. That's pretty straightforward. Oxygen in a compound takes an oxidation state of -2, meaning carbon is +4 to take into account the neutral net zero charge on this carbon dioxide molecule. And oxygen -2, and similarly hydrogen +1. So that's simple enough. But there are a few really interesting notes to observe in this chemical reaction. The first being that carbon begins life with an oxidation state of -4, but ends up as a product from carbon dioxide with an oxidation state of +4. What does this mean? Well, we know that each oxidation number, each unit of -1, accounts for 1 electron. So going up from -4 to +4 means that carbon has actually lost 8 electrons. It's lost 8 electrons. Where have those gone? Well, we notice that hydrogen stays at +1, so we don't really want to look at that. But we notice that oxygen has gone from an oxidation state of 0 to an oxidation state of -2 in both carbon dioxide and water vapor. So if we track the progress of oxygen in this chemical reaction, this redox reaction, we see that oxygen has actually gained 8 electrons. It's gained 8 electrons because its oxidation state has gone down, so each oxygen atom has gained 2 electrons, so it's gone from 0 to -2, and because there are 4 oxygen atoms, we see that 4 times -2 is -8, meaning the oxygens in total have gained 8 electrons. And we can describe this process, this transferal of electrons, in a device or a tool called the half reaction. We can write some half reactions here. And these half reactions are just going to explicitly state where the electrons go or how they move. And so we see carbon, in moving from methane and changing life from methane to carbon dioxide, carbon gives off 8 electrons. We see here that it lost 8 electrons, where here are those 8 electrons. Similarly, oxygen picks up those 8 electrons, it gains 8 electrons, in its journey from elemental oxygen gas to carbon dioxide and water vapor. And again, these little reactions, they don't have to be balanced, they just explicitly state where the electrons go, are known as half reactions. And so we described what happened to carbon and oxygen in terms of gaining and losing electrons. But there are really nice formal terms which we can use to describe what happened in this redox reaction. And those terms are the following. We can say that carbon is oxidized in this reaction. Carbon is oxidized. So oxidized just means losing electrons or increasing in oxidation state. And oxygen is reduced. Oxygen is reduced. Its oxidation state has gone down. At the same time, it's gained electrons. So gained electrons, oxidation state has been reduced. And we can extend some of this vocabulary to describe how carbon and oxygen actually participate in this chemical reaction. Carbon is oxidized, oxygen is reduced. At the same time, carbon is the reducing agent. By giving up electrons, it allows oxygen to pick up those electrons and become reduced. Similarly, oxygen, as the element which is reduced, acts as the oxidizing agent. By picking up electrons, it allows carbon to release those 8 electrons, and so it does the oxidizing just as carbon does the reducing. And moving right along, yeah, this may seem a little irrelevant. It is an oil rig, but oil rig is actually one of the most useful mnemonics, in my opinion, in all of chemistry. We can define oxidation. We can say that oxidation is loss of electrons. Reduction is gain of electrons. You'll notice that the OIL, RIG correspond to the letters in oil rig. But this is kind of counterintuitive. You think reduction, you think, oh, decrease. But it's actually a decrease in oxidation state. Remember, by adding electrons, you're decreasing the oxidation state. Similarly, by losing electrons, you're increasing your oxidation state. So oxidation is loss of electrons. Reduction is gain of electrons. And just to summarize what we just said, we can say oxidation is an increase in oxidation state, while reduction is a decrease in oxidation state. It's a gain in electrons, but a decrease in oxidation state. And now we're ready to define what a redox reaction is. And it's going to be a little anticlimactic, I apologize, but a redox reaction is one that just involves, oxidation and reduction, and therefore it involves the transfer of electrons between different kinds of atoms. And in fact, the term redox is just a contraction of reduction and oxygen. And unfortunately, one of the most notoriously difficult things to do in all of chemistry is to balance a redox equation. But we're going to try and break it down into a few simple steps, which hopefully will make the process a little less painful. So let's just dive right in. The first thing I suggest we do when tackling a problem like this is to assign oxidation states to each element involved in the reaction. We'll do this rather quickly. We're getting quite good at this by now. So we know oxygen takes an oxidation state of -2, meaning lead is +2, hydrogen +1, giving nitrogen -3. Remember, we're accounting for the net zero neutral charge on all of these compounds. Elemental nitrogen, of course, takes 0. Oxygen in a compound, -2, +1 for hydrogen, 0 for elemental lead. The next thing we do is we look for changes in oxidation number. We look for changes in the number of electrons to see where electrons are lost and gained. The first thing I notice, starting from the left, lead begins life as +2, ends as a product as 0. So we see that here lead gains 2 electrons. Lead gains 2 electrons. It's reduced, and therefore its oxidation state goes from +2 to 0. At the same time, I see that oxygen stays the same. Nitrogen goes from -3 to 0. -3 to 0. So nitrogen actually loses 3 electrons. Now you notice here these numbers are not the same. Way back here in our first example, carbon lost 8 electrons, but oxygen gained 8 electrons. So there was no net change in the number of electrons. That makes sense. According to the law of the conservation of mass, we can't just create electrons or invent electrons on one side of this chemical equation. They have to be balanced. You can think of the law of the conservation of mass in terms of redox equations as the law of the conservation of electrons. We have to have the same number of electrons lost as gained. They can't just appear or disappear into the ether. So to balance these, we're going to treat them as we would atoms in balancing a chemical reaction. We're going to multiply this gain by 3 and this loss by 2. And in doing so, we're just going to add coefficients to the atoms involved. So we've stuck a 3 in front of the lead, meaning that lead now gains 6 electrons, a 2 in front of the nitrogen, meaning that nitrogen now loses 6 electrons. So we've balanced the electrons in this case, and we can now proceed as if this were a regular chemical reaction, balancing the type of elements on the reactant side with the product side. So here we go. We should be pros at this by now. We've got 3 lead on the reactant side. We've only got 1 lead on the product side, so we're going to have to multiply by 3. Stick a 3 there. Oxygen, we've got 3 oxygens on the left-hand side. We've only got 1 oxygen on the right-hand side. So again, we're going to multiply by 3, put a 3 in front of water. Next, we've got 2 nitrogens here. That's good because we've got diatomic nitrogen gas over here. So 2 nitrogens, 2 nitrogens. And then finally, hydrogens. We've got 6 hydrogens over here, and that works because we've got 6 hydrogens over here. So this turns out to function in a 3 to 2 to 1 to 3 to 3 ratio for our coefficients, and this redox equation is now balanced. And just to recap what we just did, here are 4 simple steps for balancing a redox reaction. The first thing we're going to want to do is write out the oxidation states. That's what we did here, remembering to always balance the charge on each compound or each molecule, making sure that the oxidation states sum to the charge on that compound or molecule. Next, we want to determine the total number of electrons gained and the total number of electrons lost. So we're going to do so by looking at changes in oxidation states. So we noticed here that lead changed from +2 to 0, nitrogen from -3 to 0, etc., etc. And we can use that to figure out the total number of electrons gained and electrons lost. Of course, next thing we have to do is balance the number of electrons gained and lost, because as I said, we can't just invent electrons on either side of the equation. They have to be the same number lost as there are gained. And finally, once we've balanced the electron bit of the redox reaction, we can just treat this chemical equation as we would any other, and just balance the different kinds of elements on each side of the equation, as we did here, as we did here. The real painful bit are these first 2 steps, figuring out what the oxidation states are and then how they change, figuring out how to balance those electrons, keeping in mind that we have to have the same number of elements of each kind of element on each side of the equation. And now, here's a pretty challenging problem for you. If you go to Crystal Springs, you might know the legendary physics teacher, Mr. Woosnam. He would call this one a doozy, so if you can tackle this problem, my hat's off to you. But why don't you give it a shot and then come back in a few minutes after pausing this video and we can go over the answer. So welcome back. Again, my congratulations if you actually figured out this problem. It's quite the doozy, as I said, but we're going to do our best to figure it out. And so we're going to follow our steps, first step being to assign oxidation states to each element in this chemical equation. We'll go through this quickly. Elemental copper is 0, oxygen -2, the charge on this nitrate ion is -1, so we're going to have a +5 for that nitrogen, and then a +1 to make this total HNO3 have a charge of 0. Same thing, the nitrate ion is going to stay the same, so -2 +5. This nitrate has a charge of -1. There are 2 of them, so this copper now has an oxidation state of +2. Next, oxygen in a compound takes -2, giving nitrogen +2, oxygen -2, hydrogen +1. Now we're going to look for changes. We're going to look for changes in oxidation state to figure out the total number of electrons gained and lost. First thing I see is copper. Copper goes from 0 to +2, meaning it lost 2 electrons. Lost 2 electrons. We've gone up by 2. Copper's been oxidized. And here's the little trick. We see that nitrogen, well, some nitrogen has stayed at +5. Stayed at +5 here, it's still +5 here. But this nitrogen has become +2. This nitrogen has become +2. So this nitrogen involved in this NO molecule right here has actually, let's see, it's gained 3 electrons because it's been reduced. Its oxidation number has decreased by 3. And now we need to go about balancing, as step 3 states, balancing the number of electrons lost and gained. And we've done this before. We're just going to multiply this by 3 and this by 2. But the placement of the coefficients in this case is important. We can of course put a 3 here. That's fine. But we only want to change the coefficient in this case of the nitrogen that actually gains electrons. We don't want to mess with this nitrogen here because it stays at +5. It doesn't have any change in the number of electrons it has. So we want to stick this coefficient here just to make sure that we increase the number of gained electrons to 6. Now we've lost 6 electrons, we gained 6 electrons. So the electrons are balanced. So now we can move forward and just balance the number of elements on each side of the reaction. And this is still a bit challenging, so we'll try and make our way through this as slowly as possible. So we've got 3 copper on the reactant side. We've only got 1 copper. Let's see, 3 copper, 1 copper. So we need to plop a 3 in front of this formula unit. Next, let's look at nitrogen. Let's look at nitrogen, and we've got, let's see, N times 2 times 3, so 6 nitrogens here, plus 2 nitrogens here. So we've got 8 nitrogens on this side, but only 1 nitrogen on this side. So we've got to multiply that nitrogen by 8. So we're going to plop an 8 there. Next, we can look at hydrogens. So we've got 8 hydrogens over here, only 2 hydrogens over here. So 8 hydrogens, 2 hydrogens. We're going to want to multiply these hydrogens by 4. That's going to give us 8 hydrogens. That's going to work. And finally, we're going to look at oxygen. So we have 24 oxygens over here. On this side, let's see, we have 6, 18 from this, which this contributes. We've got 2 here and 4 here, giving us a total of 24. So our answer, the ratios of our coefficients are going to be 3, 8, 8, 2, 8. And that checks out, both the electrons and the total number of elements. So good work, and I look forward to seeing you in the next video.